Hello everyone, I'm Mathieu Gascon, student at the University of Montreal, and I will present you the paper Complexity and Algorithms for MUL-Tree Pruning, written by Ricardo Dundee from the University of Bergamo, Nadia Al-Mabrouk from the University of Montreal, and myself. In this paper, we consider problems related to multiply labeled trees, or MUL-trees. More specifically, we are interested in pruning leaves of MUL-trees in a way leading to single labeled trees, satisfying some properties. Although present in various fields, MUL-trees are relatively little studied compared to single labeled trees, as most problems involving single labeled trees become NP-hard when generalized for MUL-trees. Our main motivations were the inference of a species tree and the super reconciliation of a set of gene trees. In this paper, we consider two problems. The first one is pruning a set of MUL-trees in a way leading to a set of label isomorphic trees. And the second one is pruning a single MUL-tree in a way minimizing the reconciliation distance with a given species tree. Our first motivation is the species tree inference. So, for example, if we are given two gene trees, T1 and T2, from different gene families, we want to find the corresponding species tree. In this case, the species tree S may be a good corresponding species tree, as it is displayed by both the trees T1 and T2. One way to find this species tree S could have been by pruning leaves of T1 and T2, leading to the species tree S. Our second motivation is the super reconciliation of a set of gene trees, but before talking about it, I will first introduce the reconciliation approach. Given a gene tree T and a species tree S, the model of reconciliation consists in embedding the given gene tree into the species tree. The incongruence between the two trees is explained through loss and duplication events. Here, the rectangles represent duplication events, the circles represent speciation events, and the dotted lines represent losses. In particular, minimizing duplications and losses is done through the LCA labeling, where each node of T is mapped to the lowest common ancestor to the species of which the genes below the node of T belongs to. So, for example, if we look at this node here, the genes below it are C, A, and B. So we find the lowest common ancestor of the species corresponding to those genes, so A, B, and C, which is gamma. So this node is mapped to gamma. A node of T is a duplication node if and only if it has the same label as one of its children, and it is a speciation node otherwise. Losses are inferred accordingly. In the reconciliation approach, each gene family is considered independently, assuming an independent evolution. This is too restrictive for genes organized in syntonic blocks. In the super reconciliation approach, we instead consider each gene families at the same time. Here, for example, we have 4 syntonies, A1, A2, B1, and B2, across 2 species, A and B. We also have a species tree for those species, and 3 gene trees for the gene family red, green, and blue. We then embed a syntony tree, which is a super tree of the gene trees, into the species tree. The incongruence between the two trees is now explained through segmental loss and duplication events. In the current model of super reconciliation, the syntony tree must be a single labeled tree. Hence why we may want to prune leaves in the gene trees to obtain a single labeled syntony tree. The first problem we looked at, which is directly related to our motivations, is the MUL-Tree set pruning for consistency problem. Given a set M of MUL-trees on an alphabet X, is there a perfect pruning of each tree of M resulting in a set of consistent trees. By perfect pruning of a tree, we mean a single labeled tree obtained from a MUL-Tree by pruning leaves, leading to a tree containing each leaf label initially present in the MUL-Tree. And by consistent trees, we mean trees that are label isomorphic. For example, here we have the two MUL-Trees T1 and T2 on alphabet X, and we see that if we prune the leaves in gray in each trees, both the trees T1 and T2 become the tree T3, also on alphabet X, which is a perfect pruning of T1 and T2. So in that case, there exist perfect prunings of T1 and T2, resulting in a set of consistent trees, because both the trees become the same tree. We studied the complexity of the multi-set pruning for consistency problem, and we found that a related problem relying on pruning all subtrees under duplication nodes rather than individual leaves has been shown NPR'd by Skornavaca et al. In 2009. Here, it is easy to see that the multi-set pruning for consistency problem is in NP, because given a choice of leaves to prune in each tree to obtain perfect prunings, the pruned trees can be obtained in polynomial time, and then we can use existing algorithms, also in polynomial time, to check whether the pruned trees are consistent or not. We then proved that the problem is NPR'd by reduction from 3-set, and our reduction shows that the MUL-Tree set pruning for consistency problem is NP complete, even if each label is present at most 3 times in each tree. As the first problem we looked at is NP-hard, we thought we could get an easier problem by considering only one gene tree at a time. This led to our second problem, the multi-pruning for reconciliation problem. Given a gene tree T, a MUL-Tree, and a species tree S, single labeled tree, both on alphabet X, find a perfect pruning of T, minimizing the duplication distance with respect to S. The duplication distance is the number of duplication nodes of the gene tree after reconciliation with the species tree S and is given by the LCA labeling. For example, here we have a gene tree T and a species tree S with initially a duplication distance of 5 because there is 5 duplication nodes in the reconciliation. And we see that we can obtain a perfect pruning of T, minimizing the duplication distance by pruning all leaves in gray. After pruning, we obtain a tree with duplication distance 1 because only the duplication node in white is remaining. We studied the complexity of the multi-set pruning for reconciliation problem in its decision version. So given a gene tree T and a species tree S and a positive integer key, is there a perfect pruning of T with duplication distance at most key with respect to S? Unfortunately, this problem is also NP-complete. It is easy to see that the problem is in NP because given a choice of leaves to prune in the gene tree T, we can obtain the pruned tree in polynomial time, and then we can compute the LCA labeling and obtain the duplication distance also in polynomial time. We then showed by reduction from set cover that the problem is NP-hard and that it is also W2-hard when parameterized by the duplication distance key. We then developed a heuristic to solve the MUL-Tree pruning for reconciliation problem based on solving an intermediate problem, the MUL-Tree duplication removal problem. Given an LCA labeling of T with respect to S and a duplication node X, is there a pruning T star of T obtained by fixing X? By fixing X, we mean such that the node X is either removed from the tree or converted to a speciation node. The pruning T star of T must contain each leaf label initially present in T. For example, we could ask whether there exists a pruning T star of T obtained by fixing the duplication node in white And here the answer would be yes, because we can prune the leaves labeled E, F, and D under the duplication node in white, thus removing the duplication node and thus fixing it. And we can do so because the labels E, F, and D are present elsewhere in the tree. If we now consider the tree T after we prune the leaves in gray, it is now impossible to find a pruning T star of T obtained by fixing the duplication node in white, because the labels E, F, and D aren't present elsewhere in the tree, so we can't prune the leaves below the duplication node in white. We developed an algorithm called the Dupreem algorithm that solves the MUL-Tree duplication removal problem. That algorithm works by looking at different cases to try to fix the given duplication node. In cases 1 and 2, the algorithm tries to remove a full subtree rooted at either the left or the right child of the given duplication node. Doing so would then remove the duplication node, thus fixing it. If we take the same example as before, with now the duplication nodes numbered in blue, and we look at the duplication node number 5, we see that we can fix it by removing either subtree rooted at its left or right child. So for example, if we remove the one on the right, the duplication node is removed and thus fixed. In cases 3 and 4, the algorithm tries to prune the leaves below the duplication node in a way that the children of the duplication node are now mapped to the children of the node in the species tree S, to which the duplication node is mapped to. For example, if we look at the duplication node number 1, which is mapped to K, we would like to prune leaves below it so that one of its children is now mapped to I and the other one is mapped to J. As its right child is already mapped to J, we look if it's possible to prune leaves below its left child to map it to I, and in that case it is possible by pruning the leaves in gray. Once the leaves in gray are pruned, this node is now mapped to I, and the duplication that we wanted to fix is now converted to a speciation node. In cases where the previous cases are not possible, the algorithm tries to prune leaves below the given duplication node so that the given duplication node is now mapped lower in the species tree S, and then the algorithm iterates and try again the different cases. For example, if we look at the duplication node number 2, we can't use any of the previous cases to fix this duplication node, as the label C is present only once in the tree, and the label B is also present only once in the tree, so we can't prune those two leaves. But it is possible to prune the leaves in gray so that the duplication node number 2 would then be mapped to I, and then we can try again the previous cases. Once the leaves in gray are pruned, the duplication node number 2 is now mapped to I, and then we see that the case 4 is possible if we prune the leaf labeled A in gray. We can convert the duplication node into a speciation node. If for a given duplication node for which we can't use cases 1 to 4 to fix it initially, it is possible to use the case 5 or 6 to map it lower in S. But if then we still can't fix it with cases 1 to 4, the algorithm will continue to iterate and to map it lower and lower in S until it becomes possible to fix it with one of the cases 1 to 4, or until it becomes impossible to lower it further in S. In the latter case, it is then impossible to fix the duplication node. Here's another example in which the duplication node number 3 can be fixed with cases 1 through 4. As we said before, in some cases, fixing one duplication node can fix other duplication nodes in the process. As our goal is to minimize the number of duplication nodes, our algorithm will choose the way fixing the most duplication nodes when there are multiple ways to fix a given duplication node. In this particular example, our algorithm will try all cases 1 through 4 and select the one that fixes the most duplication node. Case 1, in which the algorithm removes the whole subtree rooted at the left child of the duplication node number 3, fixes 3 duplication nodes. Case 2, in which the algorithm removes the whole subtree rooted at the right child of the duplication node number 3, fixes 1 duplication node. Case 3, in which the algorithm removes the leaves labeled by A in gray, fixes 2 duplication nodes. And finally, case 4, in which the algorithm prunes the leaves labeled by D and B in gray, fixes 2 duplications nodes. The algorithm then chooses the case 1, as in this example, it fixes the most duplication nodes. The Dupreem algorithm can easily be implemented to work in quadratic time, but we found that we can obtain a linear time algorithm by preprocessing the species tree S so that we can decide in constant time which cases are possible at a certain iteration. Thus, the Dupreem problem can be solved in O of n, where n is the size of the gene tree T. Here is the pseudocode of our MUL-Tree pruning for conciliation algorithm. It is a greedy algorithm in which at each step we try to fix all duplication nodes of the gene tree with the Dupreem algorithm. And out of all the duplication nodes that we can fix, we remove the one duplication node leading to the lowest number of remaining duplication nodes. The algorithm then iterates with the newly obtained gene tree until there are no more duplication nodes that we can fix. It is possible that the algorithm outputs a tree that is not a perfect pruning of the input gene tree, but in that case, we can prune leaves from the outputted tree to transform it into a perfect pruning of T. And we can choose any way we want to do that, because regardless of how we prune it, the number of duplication nodes will remain the same. We can now look at the execution of the MUL-Tree pruning for conciliation algorithm on our first example. The algorithm will first look at each duplication node and check if they can be fixed using the Dupreem algorithm. In that case, all 5 duplication nodes can be fixed, so the algorithm will choose the one that fixes the most duplications nodes in the process. So here it will be the duplication node number 2, as it fixes 3 duplications in the process. We can fix it as we saw previously. First by mapping it to I in the species tree and then convert it to a speciation node. Then there will be only 2 duplication nodes remaining, duplication node number 4 and 5. Then again, we check if we can fix them with the Dupreem algorithm. In that case, the duplication node number 4 cannot be fixed, as we can't prune any of the leaves below it. But it is possible to fix the duplication node number 5 by pruning either of its children. After that, the only duplication node remaining is the duplication node number 4, which cannot be fixed. So the algorithm ends and returns the tree. In that case, we see that the MUL-Tree pruning for conciliation algorithm returns the optimal tree, with only 1 duplication node remaining at the end. Let's now look at the complexity of the MUL-Tree pruning for conciliation algorithm. In the worst case scenario, the algorithm would fix 1 and only 1 duplication node at each iteration until there are no more duplication nodes. As checking if we can fix a given duplication node is done in time O of n with the Dupreem algorithm, the time complexity of the MUL-Tree pruning for reconciliation algorithm is in O of n times t squared, where n is the size of the gene tree T, and D is the number of duplications of the LCA labeling of T. As we were working on the multi-pruning for reconciliation problem, we noticed that for some duplication nodes, the answer to the Dupreem problem is obviously true, and there exists an optimal perfect pruning with those nodes fixed. If we look at the example here, we have a gene tree T and a species tree S, and we see that we have one duplication node here, and it is obvious that we can fix it by pruning either of its two children. So before using our algorithm on gene trees, we first pre-process them to fix those duplication nodes for which the optimal way of fixing them is obvious. For the results, we run the MUL-Tree pruning for reconciliation heuristic on trees from the Ensemble genome browser to test its accuracy against the optimal solution. The optimal solution for a tree T is obtained with an exact exponential algorithm, which simply tries all possible perfect prunings of T after preprocessing. To keep the execution time of the exact exponential algorithm reasonable, we restricted the species to a set of 12 silverside fishes. There were 16,369 trees containing at least 2 of our species in the dataset. The total number of duplications for all gene trees after the preprocessing is 49,756. This number is reduced to 22,532 after using the multi-pruning for reconciliation algorithm on all gene trees. So we see that the MULTree pruning for reconciliation algorithm manages to fix a lot more duplications than the preprocessing alone. After, for comparing the result with the exact algorithm, we only process trees with at most 32 leaves after the preprocessing to keep the execution time reasonable. Out of those trees, the preprocessing did not return an optimal solution for 4,570 trees. For those 4,570 trees, the percentage of trees for which the MULTree pruning for reconciliation algorithm returned an optimal solution is 74.6%. The percentage of trees for which the algorithm returned a solution with one more duplication than the optimal is 21.3%. The percentage of trees for which the algorithm returned a solution with 2 more duplication nodes than optimal is 3.7%. And the percentage of tree for which the algorithm returned a solution with 3 more duplications or more than the optimal is 0.4%. The algorithm never returned a solution with more than 4 more duplication nodes than the optimal solution. This figure illustrates the accuracy of the heuristic on the considered trees depending on the number of duplication nodes of the input trees after processing. The x-axis is the number of duplications the preprocessed input trees, and the y-axis is the mean for all input trees with deduplications after preprocessing of the ratio of the number of duplications remaining after the optimal algorithm by the number of duplications remaining after the MULTree pruning for reconciliation algorithm. If there is no duplication remaining after the MULTree pruning for reconciliation algorithm, we consider the ratio to be 1 because it is the optimal solution. We see that the right part of the figure looks a bit odd, and that is because we don't have a lot of data for those numbers of duplications. We see that the accuracy of the heuristic does decrease when the number of duplication nodes increases in the input trees, but it still managed to return good solutions, having most of the times less than 40% more duplication nodes than the optimal solution. In conclusion, both the MULTree set pruning for consistency and the MULTree set pruning for reconciliation problems are NP-complete. The decision problem for the removal of a single duplication node is solved in linear time. The MULTree pruning for reconciliation algorithm computes a pruning t star of t in time O of n times d squared with generally good accuracy compared to the optimal solution. And finally, we now consider grafting leaves to trees instead of pruning leaves. in case where the trees we have would lack information. One interesting problem could be, given a set of MUL-trees, to find the number of leaves we have to graft to make the set consistent. Thank you for listening.